Thank you so much for having me. Thank you for doing this so fast. As a conference organizer myself, I know how much of a headache this is to create a conference like this. So really kudos to you, the organizers. That's not obvious at all. So 2 years ago, I helped a friend test a project, and it showed this possible way to hack a CAPTCHA model by brute forcing from scratch using Go in just a few hours. And the way to go about this was inspect the model, load the model, try to log in with a pin, which is 0000, open a cookie jar, get a CAPTCHA, pin, wrong pin, next one, and then go back to the CAPTCHA and so on. And there's a big write-up about this, and the GitHub repo is also available. It was done all in Go and in TensorFlow, used machine learning. Pretty interesting. This is a talk I gave in the past already. Maybe somebody recognizes the slides. But I'm not a machine learning person. I'm not a data scientist. I studied computer engineering. I designed chips, and now I'm doing cool things with databases. Yet I get to do in my free time cool things with machine learning using only my knowledge in Go. In the past, I had the chance to give talks about machine learning like this one using Go. And I had the chance to give talks about using Go for system programming, so not just as a backend language, but actually as a systems language. And this talk is kind of bringing those two together, and it's connecting the dots in a nice way. I will be describing the beginning of my journey of building an end-to-end system for machine learning from scratch, using only Go and my very little knowledge that I have. Small asterisks, it will not include building the model from scratch. Let's try to see how this polling option works. Is there any machine learning engineers in the crowd? Is this something we can do with polling? Maybe somebody from the organizers can help out.
Natalie, I'm sorry. What help do you need?
I would like to do a poll if there's any machine learning engineers in the crowd.
Maybe guys and girls, just raise your hands if you are.
Oh, well.
Yeah, there is a separate button to raise the hand. 3,
2, 5.
Right.
Not much really. 7.
That's almost 10%. Oh, I'm afraid I might need to exit for a second the keynote because the Zoom chat popped in the middle of my screen and I cannot see my mouse to move it. Sorry. There, escape helped out. Cool, okay, so there's some machine learning engineers in the crowd. I guess most of the people are backend developers. If you can vote.
Raise your hands. Yep.
A lot. a lot of people.
Yep. All right. A DevOps or a platform engineer, SRE?
Something between backend developers and machine learning experts, I would say.
Something like 15?
2, all right. So mostly backend engineers, then some machine learning engineers, and a very few DevOps people. Yeah?
Less machine learning than DevOps.
Understood, all right. That's a good mix of skills then, good. During the next 45 minutes, there will be moments where some people from some group will say, ah, that looks familiar. All right, and there'll be some moments where some people will say, wait, what is that? And by the end of this talk, I hope that you will go to the next coffee break or the lunch break, understanding the end-to-end part of machine learning production systems with a lot of this passion that comes after, oh my God, I know so very little about this, I want to learn more. And some logistical requests. I'll keep asking questions. Please keep answering them. please help the organizers to do this as fast as possible by trying to be interactive. Replying with a plus or with a yes in the chat to questions is great. I will promise that I'll try to keep this mostly a yes/no questions. And if you learn anything cool, please share. In the screen, you can see the social media handles of the conference. So it's on Twitter, there's a tag and there's a hashtag. So what is machine learning? Basically, it's the creation of algorithms that can modify itself without human intervention to produce this desired output by feeding itself through structured data. We saw in the definition that this is a subset of AI. What is AI? I saw this beautiful picture in a tweet of a person goes by the handle, the Alex Freeman Twitter, and it's pretty much everything. It goes from text to speech to planning to assisting with software to doing robots to do natural language processing, computer vision. It's pretty much a lot of what's going on with computers. So the official definition is that in computer science, artificial intelligence is intelligence demonstrated by machines, unlike intelligence that is displayed by humans, that is called natural intelligence. And the term is described to describe computers that mimic cognitive functions that humans associate with the mind, such as learning and problem solving. This part is probably going to be a little bit familiar to the machine learning engineers in the crowd, how to ML. And if to go over the steps real quickly, you define the problem. So what is it that you're solving? You're gathering your data. So for the sample set mostly, for example, if you're predicting numbers, you're preparing the numbers. You prepare the data, so you clean it, you randomize, and you split it 25-75 for training testing. You choose a model based on the learning task, on the input time, and a possible number of categories. For example, if you're recognizing digits, it's going to be 10 possible number of categories. If you're recognizing faces, it's going to be thousands, millions. You train the model by assigning random values. You predict the trained data, and you adjust the weights, and you do this in an iterative process. And then you evaluate the model using this 25% of the test data that you set aside in step 3. If it looks good, you tune the hyper parameters or fine tune them. Maybe you need to change the input, maybe you need to retrain. And once it's ready, you go ahead to predict. So that's it, let's do machine learning. TensorFlow is a very common tool for this, a great open source platform for this. End-to-end machine learning solutions used for machine learning applications like neural networks. And it's made of tensors, which is a generalization of vectors and matrices to many dimensions. It doesn't have to be 2 or 3 dimension. And you define this with a data type, can be integer, string, or anything else. And the second property that it has is the number of dimensions, the number of values per dimension. And you take this data and you flow it through the graph or the model, which is a set of nodes or the mathematical operations that's happening on your data. And the tensors basically flow through that. And at any point you can inspect each node and see the intermediate value of the calculation. That's pretty much why TensorFlow is called TensorFlow. The nice thing about it is that it's community driven and it's becoming really friendly for developers, also for Go developers. There are specific tools there like AutoML, which lands you directly in step 8. So right after step 7 that you're ready to predict, you just do some drag and drop of pictures and labels and you're all set. You can use the TensorFlow Hub, which is a GitHub repo for modules. So people who, for example, finished their PhD and came up with this new interesting model, they would just upload it there and you can use it. This lands you at step 5 where you have a model and now you need to train it. And there's also out-of-the-box solutions that are built on top of TensorFlow. So this talk is about infrastructure for machine learning, right? This is a great article from 2015 that is talking about all the potential issues behind a quickly hacked machine learning system. 5 years later, this is still pretty overlooked and still very, very relevant. If you want to take a screenshot or a picture with your phone and Google it later, it's available publicly, and I think it's very interesting. A production machine learning system involves a significant number of components. There is a lot to it than just the machine learning algorithm. The machine learning code at the heart of the real world production system, it accounts about 5% of the code of the system. Give that a moment to sink in. The production system devotes the considerable resources to input data. It collects it, it verifies, extracts features. There is a serving infrastructure. There is monitoring and many other practical parts. So all that we talked until now, TensorFlow or building models and so on, imagine this is just 5% of the code of the real system. Now we will dive into architecture components, and it's going to be a lot of information. I intentionally went fast through the first part of introduction to machine learning to represent that this is about 5% of all the code that we need. From now on, it's going to be even more. Make sure you're ready. Take a deep breath. It's definitely good for the brain. Now, as an engineer, I like giving practical hands-on advices, and that many times means mentioning specific tools. I always try to mention open source tools. I try to mention tools that work with Go, but this is by no means a comprehensive list, and there's many, many other solutions and many, many architectures out there. So let's start with a very common one, Hadoop. Probably you heard the name. Quick show of hands, does anybody know what does this stand for? If you do know, maybe you can type what does it stand for already.
Yeah, I see some hands.
Well, please type the answer. Any guesses?
Natalie, can you read it?
I cannot see my mouse move when I have a keynote in full screen, so no, I would appreciate your help.
Distributed FS, Yellow Elephant, Hadoop, Distributed Compute System.
But what does the name, like why Hadoop, why not something?
System.
Does the H stand for something? Does the A stand for something? I think maybe by now there was even enough time to Google this. So it stands for High Availability Distributed Object-Oriented Platform. That's why the name Hadoop. And as an Apache project, it's probably appropriate to use the right logo with the Apache logo in this. And so Hadoop is a collection of open source utilities that facilitate using a network of computers, of many computers, to solve problems involving massive amounts of data. It provides basically the software framework for distributed storage and processing of big data, and it's relying on the MapReduce programming model. This means it's a set of open source programs and procedures. Anybody can use this as a backbone for their big data operations. And it's made of 4 different modules which carry out different tasks that you need for a computer system to handle big data analytics. The first most important one is, of course, the HDFS, the distributed file system, which allows data to be stored in an easily accessible format across a large number of linked storage devices. Then there is the MapReduce. This provides the basic tools for poking around in the data, and it's named after the 2 basic operations that the module carries out. Map is basically reading the data from the database and putting it in a format that is suitable for analysis. Reduce is performing mathematical operations like counting the number of people under the age of 30 in your customer database. Next is the Hadoop Common, which is providing the tools you need for the operating system to read the data stored under the HDFS. And the last one is the Yarn, which is slowly being less and less used, managing resources of systems that are storing the data and running the analysis. Various other procedures, libraries, or features have come to be considered part of the Hadoop, but those are the main four. Hadoop is a very flexible system, and that means that companies can just choose to modify their data system as they need changes. It's cheap, it's ready available parts, and you can kind of like puzzle your backend to handle things like data storage, data processing, and so on. And it's said that more than half of the Fortune 500 companies are using it. This slide is probably the trickiest one in this entire presentation, where I'm putting apples and pears together. And to add to that, blending in papples. Anybody heard of papples, aka crunchy gold apple pears, aka nashi? This is basically where you take an apple, you take a pear, you breed them, and it's technically called an Asian pear, but this is some kind of a weird mix in between. So this is used to say as a disclaimer that the next slide is really mixing terms and trying to generalize as much as possible just to send across a concept, but it's a very tricky slide. Okay, so Hadoop, you can say, is one of the ways to build a data lake. Hope you all are familiar with the term. A data lake is a centralized repository that allows you to store all your structured and unstructured data at any scale. When the data comes in different sizes and shapes, and you need different tools that make different platforms. The person who coined this term is called James Dixon, and this is how he explains what is a data lake. So other tools that you can use to build a data lake platform is the Azure Data Lake, Apache Spark, and Google BigQuery, and many others. They all have Go APIs. Next component in an architecture is a database. You can train models with the data that you have in a folder on your local machine when you learn how to do machine learning. But when you go to production, you need to store all this data. You have a lot of it. You need to share it. You need to manage it. You want to be able to access it in an efficient way. That's why you have databases. Databases is a whole world to dive into, starting from the very basic separation of SQL versus NoSQL databases. Here's some examples of databases. Of course, all have Go clients. CockroachDB is written in Go. Next, we have function as a service, aka serverless. Basically, it means taking your model once you built it and trained it and serving it to the consumers. The model is deployed to a serverless service, which is then being queried, and it both works for online and offline services. AWS Lambda, Azure Functions, Google Cloud Functions, OpenFaaS, and many other options. Then you have data governance. This makes data that is openly available, for example, across different departments, or even data that is internal to a company and you want to share with everybody. So with people outside of the company, you have to filter it, you have to mask it, you have to make sensitive data to have the right compliancy, for example, GDPR. You have to set in place data control policies. For example, what types of users can see what type of data. So those are all companies that are doing this acts of data governance for you. And an interesting question that is pretty open is, let's say you have a set of data, you trained your model, and now you have to remove some of the data. For example, because GDPR kicked in, because, for example, one of the companies that provided data for your database is no longer a client of yours and they ask you to pull out the data. What happens to the model? You removed it from the system, but you didn't really extract it from a trained model. So does it consider that you filled this request of removing the data? Is it not? So a common way to go about this is have versioning, just like in GitHub for the code, also have it for your data and for the model. And the last basic part of the architecture is monitoring. You want to monitor the performance of the model. Are the predictions mostly right? You want to model, look at the system performance. How many requests you get per minute? What is the processing time? What is the resource consumption? And you want to monitor the app. For example, doing tracing for a request through the app, how many database connections time out, and so on. And so covering all the different parts of the very most minimalistic infrastructure for machine learning, putting that together, we're going to get this bare bones infrastructure. And I will repeat that this is my personal opinion. There is no right answer or one answer here. What is that? So first of all, we have data. And we know that it comes in different types and different formats and include a lot of noise and a lot of bias. It's important to do the versioning because, as we said, for example, deployed machine learning models are part of the code. If you don't version your data, it's going to be harder to version your model. Then you want to make sure you don't store in your system anything you're not allowed to, like if you're not PCI compliant, you don't want to store credit card information. So step one is data governance. We cleaned up the data. We can build a data lake where all the unstructured and unhierarchical and unorganized data lives. And we can also store it in a database or in an object store, like where you store binary data like images, sound files, compressed text, and so on. Then we do again data governance, this time to make sure we set the access permissions right. For example, some teams don't need to be able to see addresses and phone numbers, right? They have to know that there's something in the field and maybe it matches the format of 10 digits and that's enough. Maybe you want to make your data set open source, which is always great. So this is the second step of data governance. Then we do the training. The most common tools are TensorFlow and PyTorch, and we covered TensorFlow. And people build their entire career on this one square. Please be mindful of the simplification that I'm doing in this slide. Training machine learning models is a huge deal. So let's zoom in a bit. And we know that equations have those variables. We talked about what happens in this training stage. And broadly speaking, there are two ways to train a model. There's the static offline way, and there's the dynamic online one. A static model is being trained offline. So you train it exactly once, you upload it, and this is what you have until the next time you upload a new version. A dynamic model is trained online, so data that continuously entering the system is updating the model. And there are pros and cons to each. Static model is very easy to build and test. And what you do in it is basically you make all the possible predictions in one batch, you write it to the table, and then your model is one big lookup table. The cons of it is that it only predicts things you know about. There is an update latency, and it can have problems when you need to be dynamic. For example, your flower shop, and you know that every day of the week you sell this amount of flowers. Towards the weekend you sell slightly more. So you always recommend in the weekend buy 30% more flowers. If you're not seeing a spike on February 11, 12, 13, you're going to be sold out on Valentine's Day and lose a lot of money. Dynamic model predicts on demand. It's using a server to store the model, not the results. adaptive to changing data, and it's more likely to make better predictions, but it's compute intensive, latency intensive, and this usually would put limitations on how complex your model can be, and it requires way more monitoring. Okay, back to the infrastructure. We zoomed in a little bit on the model training. Next step, serving the model. So we have it ready, we want to deploy, we want to serve it. This comes with the entire CI/CD pipeline, unit testing, integration testing, and basically everything you know from the web flow. And then we get what we came here, the inference of the output. Let's zoom in on that as well. This is this part of the how to machine learning. And here there's also two parts. There's online and there's offline. Offline inference means that you make all the possible predictions in a batch. Online means everything's happening on the server. We covered that. And it can update as the information comes in, but it requires more monitoring and more computation resources. So you're familiar with that. But the offline is that the bonus of it is that you don't need to think about the costs so much, and you can do post-verification of the predictions and maybe find less mistakes. But the con is, again, you know only the things that you're trained about. Are we done? You can guess from my question that no. The most important part is, of course, the monitoring. We want to know the health of the system. We want to know the performance of it. And now this is what I would define as the very bare bones architecture for machine learning applications. If you want to have some proportion, how bare bone compared to this slide. This is a snapshot of the artificial intelligence ecosystem for 2019. There's a person called Matt Turk. This is his Twitter on the screen. And he also has a blog where he's writing about those things. And this is still not even all the companies or the different technologies or the different branches of artificial intelligence. Let's zoom in a little bit on the different parts. You can see there's so many we didn't mention. AI ops, data transformation, cloud, dataware, data generation, labeling, cross-infrastructure solutions, search, visualization, security, streaming, orchestration, and even this list is not comprehensive. Instead of building your bare-bone architecture, you can also take some end-to-end off-the-shelf machine learning solutions. And as you might guess, I'm referring to TensorFlow again. There is a TFX pipeline, is what you see here. So TensorFlow extended. This is a sequence of components that implement a machine learning application. Let's go quickly over the different parts of it. So you start with the training and evaluation data. We said we split 75-25. Then we go to the example gen, which ingests and optionally splits the input data set. We have the statistics gen, so the second cube in the flow, analyzes and calculates statistics for the data set. Next, we have the schema gen, which examines the statistics and creates a data schema. The example validator looks for anomalies and missing values in the data set. And the transform performs feature engineering on the data sets. The trainer, as you can guess from the name, trains the model. Then comes the validation part. The evaluator performs deep analysis on the training results. The model validator helps you validate your exported modules, ensuring that they're good enough to be put in production. And the pusher deploys the model on your serving infrastructure. Now let's look at one concrete example. There's this huge company whose machine learning infrastructure I want to introduce you. I cannot mention their name today. I cannot mention their product today, because if I mention it, you will know who's the company. So I'm changing the example a little bit, and what we're going to be discussing is spam emails. This is not what they're doing. So this is my Gmail. Let's say I'm sending an email to somebody. Once I click send, there's some input about me that is being sent to their system. For example, there's the sender email, there's the receiver email, there's the title, there's the content, and there's also meta information like the header and the footer. This is the entry point to the system. This is basically going in as a web request. You can run this through the model as it is, or you can add data points like, had somebody reported this user as spam? Are there any suspicious keywords in the email? But this is a pretty slow process if you infer all those questions from this input that we have. So to put all this data, especially you want to make sure that you have many data points to make a better prediction. So what they're doing, they're running this few input data points through Aerospike, a NoSQL database, and then they pull for each of the inputs relevant information. For example, the input, who's the sender of the email of the sender, they're pulling out information. Are they new? How long have they been logged in the system? How many emails a day do they usually send? So on. For the content parsing, they're looking for some keywords that are usually correlated with emails that correlate with spam. Are there any salesy keywords? Then they create this input feature vector. In machine learning, a feature is an individual measurable property or a characteristic. A set of numeric features can be conveniently described as a feature vector. In spam detection algorithm, for example, a presence or the absence of a specific header, the email structure, the language that's used there, the frequency of specific terms, the grammatical correctness, and so on, they make this input feature vector. So in our example, is there a recognized header? This is one, so this is good. This is a familiar header and not something new. There's no official signature, so it looks a little suspicious. The structure looks mostly safe. The language looks mostly safe. There is no existence in the text. There is no special price as text, but there is something that looks close enough to prints. So maybe they wrote prints with one instead of I. And generally, the grammatical correctness of the text is getting just above average. And so from that database, they get the feature vector for the current email that I'm inspecting. And the input feature vector, so basically what we received as the sender email, email title, and so on, but enriched, is being fed into AWS Lambda. And the AWS Lambda is serving an in-house machine learning model that is served in an online way. The model was trained and built in-house. It's a big company. They definitely have the resources to have a dedicated machine learning team. This was also not written in Go. This was written in Python, because Go can do a lot of things in machine learning, but not building a model. And the model output is the percent of the chance that the email being spam. Based on that percent, it looks at the threshold, at the current threshold, and says whether we're going to mark this as suspicious as spam or not. Okay, that was quite a lot, right? So let's recap a little bit. What we covered today. We covered what's AI. We covered what's machine learning. And we covered the basic steps of how to machine learn, including TensorFlow, which is one example. We covered training and inference online versus offline. We also covered an example of what is the bare bones architecture. We also looked at off-the-shelf solution, and we looked at a concrete architecture example. Important to mention that this can be done fully in Go, except for the part of training and of building the model, sorry. All the examples, all the tools that we covered today were mostly open source and supporting Go. So This can be used as a great glue language to build the system and also to do the inferring of the machine learning model that you have. So an end-to-end architecture of machine learning model used in Go is a realistic thing to do once you have a model that's ready. A machine learning model is about 5% of the overall code of a machine learning system in production. The input data is a big and tricky part of a machine learning process. And the basic flow is you take that data, store it, train, serve the prediction, and monitor the performances. And if you're interested in following my example of building a machine learning model end-to-end in open source in Go, please follow me. I'll be updating on Twitter. Thank you very much.